At 3 in the morning, a pull request opens on a repository you maintain. 400 files changed. Tests green. Migration complete. The team that shipped it has a researcher, a coder, a tester, and a release manager. And not one of them is human. In 2026, this is just how software gets built. So today, let's take apart the machine that makes it possible. Rewind 3 years. In 2023, an AI assistant was a chatbot. You asked for a code snippet, it answered, and it forgot you the moment the tab closed. By 2024, it moved into the editor, completing whole functions. By 2025, it became an agent, something that could run commands, read files, and iterate until tests passed. But 2026 belongs to a bigger idea, orchestration. Instead of one assistant working alone, coordinated teams of agents, each specialized, each autonomous, working in parallel on the same goal. First, what exactly is an agent? Strip away the hype, and it's a loop. A language model receives a goal, decides on an action, run a test, edit a file, search the docs, executes it with a tool, then observes the result. That observation feeds back in, and the loop runs again. Perception, decision, action, feedback. The magic isn't any single step. It's that errors become information. A failing test isn't the end of the answer. It's the beginning of the next iteration. But a single agent has a ceiling, and it's easy to see. Every action it takes, every file it reads, every log it prints, piles into one context window. Give it a big enough task, and its working memory fills up with noise until it starts forgetting why it opened a file in the first place. Worse, one agent is serial. Step after step after step. A framework migration touching 1,000 files doesn't need one genius. It needs a workforce. Hence the shift. The solution is an old one. It's management. At the top sits an orchestrator agent. It doesn't write code. It reads the goal, studies the repository, and decomposes the work into a graph of subtasks, nodes with dependencies between them. Then it delegates. Each subtask is handed to a fresh subagent, with a clean context window containing only what that job needs. The orchestrator tracks progress, merges results, and replans when something fails. Its job isn't intelligence at the keyboard. It's intelligence about the plan. A typical team looks like this. The researcher explores. It maps the code base, reads documentation, finds every call site that matters, and reports back a compressed brief, not a copy of everything it read. The coder implements. It takes one well-scoped subtask and writes the change. The tester verifies. It runs the suite, writes new tests, and tries actively to break what the coder built. And the deployment agent handles the last mile. Builds, staging, canary releases, rollbacks. 4 different jobs, 4 different toolkits. And the specialization matters. A verifier that wants to find bugs behaves very differently from a builder that wants to be done. And here's where it gets fast. Independent subtasks run at the same time. Separate agents in separate sandboxes, often on separate copies of the repository. While one coder migrates the authentication module, another handles payments, and a third updates the tests. What was a serial chain becomes a set of parallel lanes. The speedup is bounded by the dependencies, the classic Amdahl's law problem. But for wide, repetitive work like migrations, the parallel fraction is huge. The second superpower is stamina. These systems run for hours, sometimes days. That requires machinery humans never see. Checkpoints, so a crashed agent can resume instead of restart. Persistent memory outside the context window, so a decision made on hour 1 still holds on hour 30. And budgets, limits on time, tokens, and actions, so a stuck agent fails loudly instead of looping forever. Autonomy here doesn't mean unsupervised. It means the supervision is designed in. Asynchronous, not constant. There's a quieter craft underneath all of this, context engineering. Agents can't just share everything. A sub-agent drowning in irrelevant detail is worse than one that starts blind. So teams communicate through artifacts, a shared plan file that every agent can read and update, task lists with owners and dependencies, and compressed briefs, summaries of thousands of lines, boiled down to the 10 that matter. Standard protocols now glue it all together. The Model Context Protocol, MCP gives agents a common language for reaching tools, databases, browsers, ticketing systems, while agent-to-agent messaging lets an orchestrator reassign work mid-flight. The result is oddly familiar. Documentation, stand-ups, and handoff notes. We rebuilt the software team's rituals in software. The heart of the whole system is the verification loop. The coder submits. The tester runs the suite and rejects. The failure, with logs, goes back. The coder fixes. The tester runs again. This adversarial handshake is what makes long autonomy possible at all, because it converts probably correct into demonstrated under test. The deeper principle, generation is easier to scale than judgment. So you scale judgment by making it a dedicated agent, one whose only incentive is to catch mistakes. So what do these teams actually ship? The unglamorous work every engineering org postpones. Framework migrations, 1,000-file rewrites from one version to another. Dependency bumps with all the tiny breakages they cause. Test coverage campaigns, and full feature builds from a spec to a merged, tested pull request. Work that is wide rather than deep, where the bottleneck was never brilliance, but hours of patient, careful, repetitive effort. And the economics are impossible to ignore. An agent team's labor is priced in tokens, and a long run can burn through hundreds of millions of them. A framework migration that consumes $50 of compute sounds expensive until you price the same work in engineer weeks. That's why the unit that matters isn't cost per token. It's cost per merged, verified task. And it has been falling fast. Inference prices dropped by orders of magnitude in 3 years, while parallel agents turn calendar time into compute spend. But yes, a swarm can also waste money spectacularly, looping on a doomed approach at $3 a minute, which is exactly why budgets and kill switches are part of the architecture, not an afterthought. Now the numbers, because this trend is measurable. Researchers at METR track the length of tasks agents can complete, and it has been doubling roughly every 7 months for years. By late 2025, frontier systems handled tasks that take a human expert multiple hours at a 50% success rate. On SWE-bench Verified, real GitHub issues from real repositories, top models climbed from under 20% in 2023 to well over 70% by 2025. Extend the doubling, and you get week-long tasks within a couple of years. But the metric that matters most is reliability, and there's a brutal law hiding in it. Chain 100 steps together, each 99% reliable, and the odds that the whole chain succeeds fall to about 37%. Compounding error is the tax on autonomy, and multi-agent systems add their own failure modes. 2 agents editing the same file, a sub-agent silently misreading the plan, coordination costs that grow with the size of the team. This is why the architecture is the story. Checkpoints, verification gates, scoped contexts. Every one of them exists to stop small errors from compounding into big ones. So where does that leave the humans? Moved up a level. Engineers in 2026 spend less time typing code and more time doing what orchestrators can't, deciding what's worth building, setting constraints, and reviewing the work. Because a pull request from an agent team is still a pull request, and someone accountable has to say yes. The skill that's rising in value isn't syntax. It's specification, the ability to state precisely what you want and to design the checks that prove you got it. The shift to multi-agent systems isn't really about smarter models. It's about structure, the discovery that intelligence, artificial or not, scales through organization. Divide the work, specialize the workers, verify everything, and keep a plan. That's not a new idea. It's how humans built everything around you. We just taught it to software. If this kind of idea interests you, subscribe. Noesis explores one idea like this at a time. Thanks for watching.